Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. If you step on inside, we're going to continue with absolute value functions. A little bit of graphing, but within it we'll be solving these these absolute value functions graphically, and then we'll be doing it algebraically as well. Now you might understand what it means to solve something algebraically, get x by itself, and we'll be doing that with the concept of how we deal with absolute value functions. But solving graphically, what does that mean? You might have done it before, not with absolute values necessarily, but with linear functions. And I'll give you a nice example. Let's just jump to the sheet right now. I'll show you what my graphs here look like with it. Let's say I have two equations. Two y equals equations kinds of things, and you can graph them. I can draw a line here and I can draw a line here, and they intersect at some point. Let me get you a unique point here like that one. Wherever these two things intersect, like this right here, there's a certain x value for them. In this case it would be x equals 3. Where they intersect there, the x location is the value that you need to substitute in for x to get the same output for y. We are trying to solve for the x that gives us the same number. Now, those generally happen in like a system of equations. You'd see a y equals this kind of equation and a y equals that kind of equation. They both have x in it, or maybe not, but they have the independent variable expression. And you graph them, you find out where they intersect, and basically what you're trying to figure out is what value of x gives you the same value for y. That's a way of solving algebraically by finding out where they intersect in that way. And that's something we can do. Now, what we're going to be presented with is not a straight up y equals set like this and that. We'll be set up with an equation that could potentially be solved algebraically on the spot. But these also both represent expressions that can be written in such a way that, if I plug in something for x, I get an output. And if I plug in something for x here, I also get an output. That being said, 5 is just a 5, right? So I got to really ask myself what value of x gets me 5 through the graph. So here's what I'm going to do. I'm going to create two different equations out of this, a y equals this and a y equals that. I'm going to graph both of them. Okay, I'm going to graph both of them, and then we'll figure out where these two intersect, what x value or x values they intersect at. And I stress the plural portion because it's very possible you'll have more than one solution. And I'm willing to bet that's why they want you to solve these algebraically, graphically first, to understand that when you solve them algebraically, oftentimes there's more than one answer. Sometimes there are no answers as well, and maybe we run into those. Not quite sure yet, we'll see. All right, so here's what's going to go on, guys. I'm going to make a y equals this equation, only I'm going to write f of x because I want to separate these two y values. I'll make sure I make mine blue and green for differentiation, but you might not necessarily have that luxury, so you might want to write f of x and g of x. We are going to find out for what value of x makes f of x equal g of x, right? For what x makes one y value equal the other y value. That's the goal. Trying to solve for x, that's it. Technically, what value of x gives you 5? So here we go. We know how to graph these absolute value functions, and if not, I do urge that you go back to one of my previous videos for it because I am going straight into the understanding that you know how to do that. So here's what we're going to do. We have a stretch factor of 1 and a vertex of flip 3, keep 2. So 3, 2. 3, 2 is my vertex of this thing. With the vertical stretch factor of positive 1, it faces upward facing graph, and we rise and run 1 in both directions of the vertex to make a V shape that goes like this. And you want to plot as many points as you fit. This is going to keep consistent with my model of what I want to say, because this time you are trying to figure out where one graph intersects with the other, and you do not want to be imprecise with your location just by roughing, plotting only a point and saying, yeah, that's pretty good, let's just go ahead and graph it, and then you end up intersecting with it at a spot that was not what you intended for it to intersect at. Now, g of x equals 5, just to kind of recap how to graph something like this, this is in y equals mx plus b form. This would be y equals 0x plus 5. How else do you get your x to go away if your slope wasn't 0? So if you have a slope of 0, that means 0 rise over some run, in this case infinite run here, with a y-intercept of 5. So if we start at a y-intercept of 5, hey, there's a point of intersection right there. We will run infinitely, but we will have a slope of 0. It won't rise at all. So basically there's a horizontal line that goes straight across like that. And that's what that graph looks like. And honestly, when we look at all 4 of these guys, that's what all of those graphs here are going to look like. We're going to have that on that side. And I want to know where these intersect. That's what we're going to find out together. So let's check it out. We intersect at, oh, where's my purple? We intersect at this place here and at this place here. Now the coordinate pairs themselves are 0, 5, and 1, 2, 3, 4, 5, 6, 6, 5. Honestly, the 5 doesn't really matter. The 5 is a part of our equation as far as what x did I have to plug in to get 5 out. And the answers are these two x values here, 0 and 6. My answers to this thing are x equals 0 or x equals 6. These are the two values of x that would actually make the left side equal the right side. And we did this graphically. We didn't use any algebra to make that happen. And if you'd like to see a double check of this, let's go ahead and plug these two numbers in and see if we actually get 5 out. Let's start with 6. If I do the absolute value of 6 minus 3 plus 2, set that equal to 5. 6 minus 3 is 3, so the absolute value of 3 gives us 3. 3 plus 2 equals 5, 5 equals 5. That seems to check out. So x equals 6 seems to work. And we're never going to use trial and error, guys. That's not a proper way of solving something algebraic. Solve an algebraic equation. We either use algebraically or graphically. Here's the alternative. We substitute 0 for x. And you're like, how can there be more than one answer? Well, because the concept of absolute values is that you can take the absolute value of a negative number and you get the same thing as if you take the absolute value of its opposite, the positive. The absolute value of negative 3 is still 3. 3 plus 2 equals 5, therefore 5 equals 5, and it works out. So there's more than one answer in the majority of these. As long as your graph has a V shape that happens to hit through your other line at 2 distinct points and you graph it correctly, then you'll have 2 answers to this thing. And there's a double check. Now, I don't know yet, so we'll see. I'll run till the end. I have 4 problems we'll do graphically, and we'll see if we run in some that have one unique solution or no unique solutions. Otherwise, expect to be running into 2 unique solutions for all of these. But it is possible to have one or none, and we will also see what that looks like algebraically, and of course, why on a graph it means that. So let's go to number 2 now. Same kind of thing, guys. This is my f of x equals here. This is my g of x equals here. So basically, you're graphing it as it says y equals. Plot the entire graph and kind of see, what happens from that. Okay, so right here on this one, number 2, we have 2 times the absolute value of x plus 1 plus 5. Let's graph that as if we have a stretch factor of 2, of course, and your vertex is at negative 1, 5. If you remember, you do flip that sign. X plus 1 means negative 1. So negative 1, 5 is like that. And then this stretch factor of 2 means we will have a upward facing because it's positive, and rise of 2, run of 1. So plot, and flip that across that axis of symmetry, plot, and we, of course, have that line. So let's, oh, I don't want an arrow there. Give me one moment. Got to reset that. There we are. Okay, there's our graph. Now, the other one is simply y equals 9. So again, that's one of those slope of 0. All of these will have that flat line, slope of 0 and a y-intercept of 9. We run across 9 horizontally on y equals, on y equals 9 right there. And that's what that looks like. Okay. So we are seeking these 2 points of intersection, specifically where the x values are. This seems to be an x value of negative 3. That seems to be one of our solutions here that gives us 9 on this side to make it equal to 9. Or we have an x value here of positive 1. And those are our 2 answers. Now, I do use the word or. You can't be both at the same time. You couldn't plug in, if there were multiple x's in this thing, I couldn't plug in negative 3 on one part, 1 on the other part. You can't be both at the same time. You're either one or the other, and either one makes a solution. So I do stress that word or when I talk about it. And when we do inequality stuff in my next video with absolute value things, I do want you to take note regarding when I use or versus when I use and, things like that. Okay, number 3. Same kind of deal here. I think we can kind of move a little more hastily if you do understand the concept of not only what I'm doing, but how to graph these as well. We have a negative 5, 4. Negative 5, 4 vertex, and because it's negative, this graph is upside down. That stretch factor of 2 means we do go down 2 over 1 in both directions, like so. And yes, please complete the graph. I know that Even when we do draw this other line of 2, you might see where it does intersect, because you can probably tell where I did actually get that plotting to happen. But still complete it, right? There's still a completist attitude toward these graphs as far as fitting what you can. It's a smart tactic. It's a smart tactic. And here's y equals 2, guys. It goes left forever. There we go. It goes left and right forever right there. And the points of intersection means we want to find the x values that represent that here. And I'm only pointing the arrows so you can see where they exist. So that's x equals -1, -2, -3, -4. So x equals -4, or x equals -5, -6 here. Those are the two values that, once again, you've substituted back in the equation. We will get 2 on the left side, 2 on the right side. And finally, we have this 3 halves here. Now, I'd like to rewrite this one, not just the f of x version of it, but I'd like to factor the 3 halves out. And again, if you were with me on a couple videos ago when you had something inside of here, the absolute value of a product, 3 halves times this, means I can split this up in 2 absolute values. The absolute value of 3 halves is 3 halves. So if I pull it out on the outside, we can reveal what our true A value is, which is 3 halves. It still is. It's still a positive. And then times the absolute value of x minus 2. And then we have a plus 3 right there. So there we go. Now we're in vertex form. And then g of x equals 2. This ain't no vertex form. This is slope. It's not even slope-intercept form, but we don't even think of this like an absolute value because it's not one. Regardless, we have those 2 right there. Let's go ahead and graph them. So this has a vertex of 2, 3 up here, 2, 3. And we rise 3, run 2. Okay, it's 3 halves taller. Rise 3, run 2, plot a point, and we keep going like that. Ooh, this is going to be one of those indicators of something else that's not quite just 2 answers. Let's see what we get here. All right, so this one here, if you can kind of anticipate what's going to happen as well, what happens when I graph y equals 2? Well, y equals 2 is a horizontal line that goes across right here. And our question is, where do these 2 graphs intersect? And of course, as you look at it, your answer is they do not. They do not intersect. And this is one of those instances of, if there are no x values that can give us the same output, then that means there is no solution to this equation. Graphically, you can tell that there is no solution if you graph them correctly and these 2 lines do not, or the 2 graphs do not intersect with each other. This is one of those setups right here. No solution. So it is possible to have no times they intersect. Now, what if, just to humor you, what if this horizontal line, or any line, right? It doesn't have to be a horizontal line. It could be another absolute value graph for all we know. But what if this line intersected right at the vertex, which means just 1 point right there? That would mean there's only one solution. So it's very, very possible that we can have this instance as well. So you'll either have one of 3 things when you have an absolute value function mixed with a constant function. Either you will have 2 solutions, and I'm not going to say it's generally the case. It depends on the problem that they give you. But I think generally they want to let you solve it. So 2 solutions will generally be the case. But then every so often they'll give you special cases with 1 solution, like you just saw, 1 solution, or what this problem was, no solution. Okay. So that's what they look like graphically, and I think that they really do want you to play with the graphs, not only because we just came off of graphs before, but also to make sense of the fact that how you can have these number of solutions and what it means to have these solutions. So there's that first part, guys. That's how we start this thing off. And now I'm going to jump forward here, and let's start talking about solving these things algebraically. Okay, solving them algebraically. So here's what solving them algebraically is all about, and I'm going to start in a very basic format, not with one of these 2 problems. Let me just kind of go off another page here. Let's say, you know, your variable's inside the absolute value, and we set it equal to something else. This is the most basic kind of form of a problem that you can have. If the absolute value of a variable of an unknown number equals 5, what you want to ask yourself in order for you to make sense of what I'm going to do next with this is, what can I take the absolute value of to get 5? And as you saw with the graphs with other things, guys, there's more than one answer to this. If I take the absolute value of 5, I get 5. But also if I take the absolute value of -5, I also get 5. Now this is kind of, I won't call it trial and error, but this is obviousness of the truth. You just kind of look and I'm just asking you the question. You know that answer and that's fine. So what we're going to do in these scenarios, guys, we're not going to write it like this. This is telling you your conditions that if you take the absolute value of something and your result is positive, that there are two different values that that thing you took the absolute value of could have been. This inside thing, and it's not always just a variable. It can be a large expression, but the thing that's inside there that includes a variable could have either been one of two values. So we look inside the absolute value and we say that that value itself could have been a positive 5, or that value could have been a negative 5. And in this case, that ends up being our two solutions there. Now, when we solve these things together, guys, we are not going to have just an x inside there, at least not that I've seen, but we'll have some sort of form of an expression. So let's look at number 5 and let's go onward here. And they're going to ask you to graph them on a number line. That just means plot where the points exist. And I think that's a leeway to when we start graphing inequalities, absolute value inequalities, in my next video regarding this. So here we go, guys. We have the absolute value of 2x equals 3. That does mean, let's look on the inside, a little introspective here. Let's look on the inside of this and say, I'm not concerned about x right now. I'm concerned about what I'm taking the absolute value of. So let me ask you it in this way. What can you take the absolute value of to get 3? You know that those numbers that you can take the absolute value of are 3 and negative 3, right? So we know that whatever we're taking the absolute value of, in this case the expression 2x, that thing, that 2x could have been a 3, right? I can replace a 3 from 2x, or it could have been a negative 3, and I take the absolute value and I get 3. So this is what we're doing. We're creating two different conditions for this graph. We say either one or the other. And then within there, we solve. We divide both sides by 2 here, and we're going to get x equals 3 over 2. Now that exact answer is 1.5. I'll make sure to note that on the number line. When we divide both sides by 2 here, we're going to get x equals negative 3 halves, or negative 1.5. I like the fraction personally, but when I graph it on a number line, I'll be sure to do that. Negative 3 halves or negative 1.5. So those are the two conditions. Those are the two answers that when I plug that into the thing, I will get 3 out. That's solving algebraically. And of course, hey guys, I could have graphed this thing, on here, and we would have gotten, 2x and 3 and said, hey, it's at 1.5 and negative 1.5, and there's that. But here's the algebraic version. Here's the number line where we're finding those x's, 1.5, negative 1.5. We just plot the points. There's no arrows or anything. Those are the only two values x can be. We're good. All right, number 6 gets a little bit deeper with this because now we have a larger expression within, right? It's not just a single term. It's also with an added constant. So once again, actually let me do this down below here. But once again, guys, we are going to be looking inside that absolute value and say, what do we have to take the absolute value of to get 3? It's not about x yet. It's about getting rid of the absolute values first by looking inside the absolute value. So what we're saying is that that expression, once again, just like last time, could have been a 3, or that expression could have been a negative 3. 1/3 x plus 4 equals negative 3. One or the other. One or the other. Now let's do this one at a time here. I know there's a fraction that might be a little daunting, but because it's not too bad. If I subtract 4 from both sides here, and I'm generally not going to write these steps right here, guys. I'm just giving you that we haven't seen kind of algebra together on these portions of the video for a while. So later on, I'll just say subtract 4 from both sides, and I'm just going to do the math. I'm not going to write that out. But 1/3 x equals negative 1. And now if I see the 1/3 means dividing by 3. So if I multiply both sides by 3, sometimes people say like 3 over 1. But if I multiply both sides by 3, I get a 3 over 3 right there, which becomes 1. And then I'm going to get x equals negative 3 there. So if a negative 3 could have been an answer to this thing here. Now, here's where you have to just be careful, because I know people tend to make assumptions on things. They tend to not speculate. They tend to make a conjecture on their own that says, well, in looking at the last problem, my answers were exact opposites of each other, 3 halves and negative 3 halves. So I'm going to guess if this is negative 3, then I'm just going to get x equals 3 here. Well, you'd be dead wrong in that assumption. There are times when it occurs. You just saw it here, and it mostly has to do with the fact that there was nothing added or subtracted to this. And also, case in point, if you look back at some of the previous problems we had here, these weren't opposites of each other. these weren't opposites of each other, and these weren't opposites of each other. So it's not like your x values are just a positive and negative version of themselves. The bitter truth of it is, guys, when I subtract 4 from a positive 3, I get negative 1. But when I subtract 4 from a negative 3, it's not like I get a positive 1. I get a negative 7. It's a way different number. And that's kind of the result in the difference there, that in this case, you're not getting just the opposite version of what's there. In this case, because there was nothing to add or subtract, you just divided yes. But there's that. Anyway, 1/3 x does equal negative 7, and I will multiply both sides by 3 again because I need to do that. So the same actions occur, subtract 4, multiply by 3, but different results can definitely come out here. And this is negative 21. So once again, there are two different answers to that thing, x equals negative 3 or x equals negative 21. You can double check them for yourselves. They should work if you know how the absolute values work and how fractions work. And you're set there. So as far as plotting these points, I think it helps that they show you a nice little scale with this thing that looks like it's going to go toward negative 21. So negative 21 is between negative 20 and negative 22. So that's going to be right there. And then negative 3 is between negative 2 and negative 4. So right there, those are our two solutions plotted. Okay, now that I've done some of those, guys, and there are my notes on that thing, let's keep moving forward with it. I get to go maybe a little bit faster. Now, the difference with these two here is there is more information than is just the absolute value thing. I can't just say either this equals 3 or this equals negative 3. Our goal was me first asking the question, when you take the absolute value of something and get 3, what could have been inside the absolute value? So if you can tell, what that kind of is going to mean is we have to algebraically do some work to first isolate the absolute value on one side of the equation. I'm not going to proceed forward until I only have the absolute value of something equals blah, blah, blah on the other side. So I have to do some steps before that. I have 3 multiplying with 2x minus 3, and do not distribute this 3 into here. This absolute value is the most protective wall that you'll ever see alongside square roots and squaring and everything like that in order of operations. Absolute value is a different animal that is not parentheses. You may not distribute. Every so often you'll run into false positives that still seem to work out. This one can be one of them. I'll tell you what, this will not be one of them. But do not distribute. Remember, our goal is to isolate the absolute value thing. Protect this. Protect this and do everything else with it. Get rid of the 3 on this side. Don't distribute it. Get rid of it. But we do this in 2 steps. We have the plus 2 that's here to start with. I want to subtract that from both sides. Start with terms that are not affecting your variable item. Your quantity here multiplied by 3. So let's subtract 2 from both sides. In this case, I won't write minus 2 minus 2. Hopefully you can kind of follow along with that. So now I have 3 times, 3 minus 2 is 1. So now I have 3 times the absolute value of 2x minus 3 equals 1. This is 3 times. I'm not asking you to distribute, but I am asking you to divide. So we are going to divide both sides by 3. Divided by 3, divided by 3, and I'll get 1/3 on this side. So I have the absolute value of 2x minus 3, and this equals 1/3. Okay. We have completed the first objective of this problem type where we are attempting to solve for x. And we have 1/3 there. Now this is my favorite go-to because of the fraction involved. We're going to have to play with it. So in order to finish this problem, you are going to have to know how to get a common denominator. And you are going to have to trust that process and how this stuff works. So here we go. As far as splitting this thing up, we look on the inside and we say, what could we take in the absolute value of to get 1/3? Those values could have been 1/3 or negative 1/3. So we either say 2x minus 3 equals 1/3 or 2x minus 3 equals negative 1/3. Genius, genius. All right. So there's the beginning of it, and we'll solve these algebraically. So I'm going to add 3 to both sides. Okay. Now, that means we're going to have 1/3 plus 3. And I do want to condense this. I want to, work this thing out a little different way. 3, if I get a common denominator, I got to multiply top and bottom by 3. So I'm going to get 9/3. 9/3 is the equivalent of 3. Let's remember that for this side. So I'm going to go ahead and add 3 on this one as well, just to kind of get it there. Negative 1/3 plus 9/3. Okay. 1/3 plus 9/3 with a common denominator will be 10/3. So now I get 2x equals 10/3. And over here, I'm going to get 2x equals 9 minus 1 is 8/3. Here's the part people always have trouble with if they don't understand their fractions. Now I'm going to divide both sides by 2. But how do I divide a fraction by 2? That looks kind of weird. Remember when we said that I didn't say these words specifically, but when I had 1/2, I multiplied both sides by 2, whatever the numbers were, to cancel them out. It's better to kind of say let's multiply both sides by 1/2 here. Because now those cancel on this side, and here we should know how to multiply fractions. You multiply straight across, boom, boom. And I'm going to do the same thing here. Dividing by 2 is multiplying by 1/2. It's reciprocal, where you flip it and times 1/2 like that, boom, boom. So x can either equal 10 over 6, which does reduce if you divide top and bottom by 2. As a fraction, it reduces to 5/3. Do not give me a decimal version of that unless you're trying to plot it on the number line. Or x equals here 8 over 6, which reduces when you divide top and bottom by 2 to 4/3. And it looks like I'm going to need some room here because I still need to do problem number 8 after this. But hopefully there's no fraction. I don't think there's a fraction on the next one. But right here, when we plot them, 5/3 is 1.6 repeating. Oh, you know what? These go by thirds. Perfect. 1/3, 2/3, 3/3, 4/3, 5/3 right there. And then 4/3 was this one right here. So those are the 2 points. Hey, thank you. They actually did something for us that was halfway decent. That's not often a trait of this book. All right. All right, so number 8 is going to be just like number 7 here in the way that we need to isolate the absolute value expression first. And I'm going to make a big stink about this one as well because I see these negative symbols. I want to forewarn you of something else that you can't do for these problems or is not a realistic expectation of them. But we want to get this thing by itself on its own side of the equation without the -8, without the plus 10, any of that. So let's do our steps here. I'm going to rewrite this here. -8 times the absolute value of -x minus 6 plus 10 equals 2. We are going to subtract 10 from both sides. -8 times the absolute value of -x minus 6 equals -8. Subtract 10, subtract 10. And then I'll divide both sides by -8. -8 over -8 is 1, positive 1. So the absolute value of -x minus 6 equals 1. Now, I haven't mentioned this part yet here, but just as a fair and forewarning, absolute value to some people does kind of mean make it positive, but you have to be very careful when you have not only expressions but variables within content, because a variable itself could be negative. There are a lot of different things. Case in point, don't turn this into x plus 6. That's not what that means. This doesn't mean make them positive like that. That is not what that means. But whatever I take the absolute value of becomes 1, so one of those numbers could have been a -1 or a +1, and that's what we're writing, guys. We're writing out the condition that the -x minus 6 expression inside there could be a 1, or the -x minus 6 expression could be a -1, like that. And that's the part that we are solving. We've been doing that the last few problems. I just want to make sure that you know with all the negatives involved, don't just make them positive. That's not what that means. I'm going to add 6 to both sides here. I get -x equals 7, and divide both sides by -1. If -x is positive 7, then positive x is -7 there. Divide both sides by -1, x equals -7. On this one here, add 6 to both sides one more time, and you get -x equals 5. Divide both sides by -1, you get x equals -5. So those are the two answers there, -7 or -5. Let's go ahead and plot those. -7, -6, -7, or -5, and we are done. Okay, how many more am I going to do? I have several more that are possible. I think I'm going to cut it short at numbers 9 through 12. There are possible others like these two as well. They just kind of get in the way. It's more of the same. At this point, once I cover this aspect of them with possible no solution cases, then I've accomplished what it is that I need, and the rest is simply enrichment. So I am going to ignore the bottom ones after this. We are already, almost a half hour in, so, we've exhausted the time that we'd like to, especially if I saw mixed numbers there. That's a no-go as far as the greater purpose here. All right, isolate them in order to determine if they can be solved. If so, find and graph. If not, write no solution. So there's very possible chance that they have no solution, and I want you to see what that means when we run into it, and what you got to avoid doing just in case you accidentally make a mistake here. This is actually, I think, is one of them. Okay, so right here. Just like before, guys, isolate the absolute value expression. I'm going to first subtract 7 from both sides, and I'm going to get 1/4 times the absolute value of x plus 2 equals 5 minus 7 is -2. Okay? All right, we're starting there. Now, a 1/4 is here, so it's like the same thing as dividing by 4. So if I want to get rid of that fraction, I'm going to go ahead and multiply both sides by 4, right? That's kind of what that part means. So now we have the absolute value of x plus 2 equals negative 8. Okay, we've isolated our absolute value expression. Now, I know what you're thinking. Let's go ahead and do what we did before. Let's create two equations that says x plus 2 equals 8 or x plus 2 equals negative 8. But you got to be super careful about the concept of what's occurring right here. Let's take a deeper look at this. Remember the question that I keep asking you. What would I have to take the absolute value of to get this number? Really, what I'm asking, what I have to take the absolute value of to get negative 8? Okay, well that's interesting. Take the absolute value of a number and get a negative? That's not a thing, right? We should only get positive, or really the sign should be, sign shouldn't be a part of this right here. The absolute value of 8, is that negative 8? No. The absolute value of negative 8, is that negative 8? No. Is there a value that we can take the absolute value of to get negative 8? No. So is there a value of x I could plug in that I could take the absolute? No. So is there a solution to this thing? No. There is no solution to this. There is nothing here that we could ever plug in for x to make this thing true, from the onset even. And what's interesting is, this is one of the other important reasons, besides everything else, why you want to isolate your absolute value thing, is this started off as positive. It looks like a positive 5. So you're like, oh, 5 or negative 5. Yeah, let's go to... No, you had to move some stuff over, figure out what it is you're actually taking the absolute value of to make that decision. And in this case here, there's no solution. There's no solution here. There's nothing to plot. There's never a time where it hits it. So we're done. So if you ever take the absolute value of something and results in a negative number, you have no... It equals a negative number. You have no solution. There's no possibility of that. When we talk about inequalities, it may be a different story. But and you'll see those on graphs when we do the inequalities. But on graphs, what we see here is an example of they don't intersect. All right, let's continue forward. Numbers 10, 11, and 12. After we saw that one, maybe we'll see something else a little special here too. No idea. So here we go. Subtract 3 from both sides. I want to start with that. So I get negative 3 times the absolute value of x minus 3 equals 6 minus 3 is 3. A lot of 3's. Divide both sides by negative 3, and you'll get the absolute value of x minus 3 equals negative 1. You're once again getting another instance of taking the absolute value of something and the results a negative number when you set them equal to each other. That is not possible. One more time, guys. This is a no solution case. Hey, these problems are a lot faster when they're no solution. Keep bringing on the no solutions. I'm totally fine with that. All right. Number 11. Now, number 11 can represent something somewhat tricky regarding how to solve because of the parentheses around this whole thing. There are one of two ways you can start it off, and I'll show you either or. I'll write one in blue. I'll write one in green, I guess. So one of them is 2 is multiplying on the outside of this whole thing. And what you can always do in a situation is you can always divide both sides by that number as long as it multiplies by the whole side. So if I divide both sides by 2, then it's gone. Remember, the 3 is also multiplying by that 2. Therefore, when I divide it by the 2, all's taken care of. We're fine, So in that situation, I would have the absolute value of x plus 4 and then plus 3 equals 6 over 2 is 3. So that's one version of what you can do to start it off before we continue forward on the problem. The other version of it is you can distribute the 2. Now you're going to say, wait a second, Mr. Robinson, you said do not distribute into the absolute value. I'm not distributing into the absolute value. I'm distributing into the quantity here that represents this term and this term here. And I say term by the absolute value set here. So what this can be rewritten as when we write it is 2 times the absolute value of x plus 4 plus 2 times 3. And you can write it like that as well. So either way, you're kind of getting into your next step there. There are different problems that do run into something like that. With the distribution, I never distributed it into the absolute value there. Either or is going to get you to the same spot. Because this one's a little closer, it's one step less, I'm going to go ahead and use this one. But if you like to keep this one available for you and understand what I just did, you could do that again. But I'll delete it. All right, so right here, I'm going to subtract 3 from both sides, guys, and we're going to get the absolute value of x plus 4 equals, 3 minus 3 is 0. All right, so I take the absolute value of some quantity, and my result is 0. What can I take the absolute value of and get 0? Well, 0. Now, this is one of those other cases. Is there no solution? No, there isn't. no solution. There's a solution, all right. But are there two solutions? Is this positive 0 or negative 0? Do we have to get these alternate signs and say that? No, 0 is neither a positive nor negative number. It kind of just is, right? We can take its absolute value, though. The absolute value of 0 is indeed 0. So that means that the x plus 4 quantity inside here could have very well just been 0. X plus 4 equals 0. No or. No solution. This is the only option. So subtract 4 from both sides, we get x equals negative 4. And that is an example, folks, of a one solution case. In a one solution, here's negative 4. In a one solution case here where on a graph that would be vertex hitting that line at one spot like that, that's what it would look like on a graph. They only hit on the vertex like that together. And that's what you would see if you graphed this one. On a XY axis like we did before. And last problem I want to do with you guys here, number 12. I don't know if there's anything real special about it other than what you just saw in this last problem here. If I add 3 to both sides, negative 3 plus 3 is 0. So I get 5 times the absolute value of 2x plus 4 equals 0. Divide both sides by 5, I get the absolute value of 2x plus 4 equals 0. It looks very similar to what we did before. There's only one condition that can do this because 0 is neither positive nor negative. So 2x plus 4 has got to equal 0, and let's find out what x value works out there. I'm going to subtract 4 from both sides. I get 2x equals negative 4, and I'm going to divide both sides by 2. I get x equals negative 2. And that's the only answer possible for that one. I only double-checked, I think, in one of my things once, way back when with the graphing one, but solving algebraically or graphically is a point that you can you can use. If you have the graphs for them and they're in vertex form and stuff and you can fit in a window range, if you like that more and you're allowed to do it, go ahead. Solving algebraically has its perks as well, but graphically kind of shows you what those solutions mean as a result. But both of them kind of work, guys. So that's what this video covers here. I hope it made a lot of sense, and I sure hope it does in the sense that I'm going to be graphing and solving absolute value inequalities as well, and I want to make sure that you know how to do those. So don't do that one until you know how to do this one. Ask questions in the comment section down below if you need to do that. So that ought to do it for this one, guys. This is Mr. Robinson. Thank you so much for watching, and take care.